And I want to welcome you to my class today. Uh, of course, today we're going to continue from where we stopped the other time in the last class. I remember on Monday we started um estimation, where we focus on, bias estimator, unbiased estimator, variance, and the mean square error. Of course, we're going to continue from there today. I remember in my last class, I actually walk you through what make an estimator to be unbiased, and of course, on how we can actually evaluate that, you know. But today, the focus is going to be, you know, um, on some common unbiased estimators that we have in statistical literature. These are common one. We got a lot of them. So, in the outline, I'm gonna focus on point estimators. Of course, in the last class, I actually um said that the estimator can be divided into two. We got a point, we got the interval. And of course, we're going to focus on point because, of course, there's no way you're going to get to interval without passing through points. So then I'm going to walk you through some common point estimator like sample mean, sample proportion, the difference of means, difference of proportions. And lastly, I'm going to walk you through what we call the asymptotic unbiased estimator. You know, initially, estimator could be biased, but maybe probably on the long run. What I mean by on the long run, maybe when the sample size is sufficiently large, a bias estimator could be unbiased. And that is what I mean by asymptotic. So I'm also going to shed more light on that. Okay, but before moving forward, I think I need to revisit the definition of unbiased and biased estimator again. If you can remember in my last class, I'm actually referring to a theta cap, okay, as a point estimator for a parameter. It's like I'm actually targeting the true value of a parameter that could be mean, standard deviation, variance, proportion, so like that. And if I go into the population and I try to, if you want to view that by way of simulation, where you go into the population several times and you actually compute the value of estimate or initial occasion, if you go, let's say you go into that 10,000 times, it means you're going to have 10,000 values. By the time I take the expectation of that, if that actually gave me the true value of parameter, then I'm actually going to say the estimator is unbiased. So estimator being unbiased, it means expected value of theta cap equal to theta. Okay? And of course, situation where that's not true, then we going to conclude that theta cap is biased. So, the takeaway is just if I want to define the bias of an estimator now, It's just going to be the difference between the expectation of the theta curve, that is the expectation of the estimator, okay, and the true value of parameter. Of course, you know when that equal to 0, okay, it means the estimator is unbiased. But if this is not equal to 0, it could be negative, it could be positive, then that estimator is said to be biased. Okay, so if that is the case now, okay, and I want to consider a situation where we want to sample from a population of interest, and we realize the distribution, or I mean the underlying distribution of the population is uniform, as you can see. Okay, y1 of the yn follow uniform distribution with the parameter 0 and theta. And of course, the probability density function is 1 over theta, as you can see. Okay, and of course, the expected value of y is theta over 2, the variance of yi is theta squared over 12. You know, let me tell you this. If we want to work with a population, we need to first have the understanding of the underlying probability distribution of the population of interest. And of course, we need to know what is the expected value of y and what is the variance of y. Of course, you know, I'm actually referring to continuous uniform. In a continuous uniform, of course, you know, in a continuous uniform where we got interval A and B, the f of x is actually going to be 1 over b minus a. And in here, you know, a is 0, b is theta. It means a is known, but b is unknown. And therefore, the focus is going to be on the theta that is unknown. And that needs to be estimated before moving forward. And that is the reason why we find ourselves here now doing this. Okay, I'm talking about continuous uniform as a parameter A and B, right? The lower, the upper one. But one of the parameters is already known to be 0, but the other one is unknown. And before I can actually do whatever in that population, this parameter needs to be estimated. But you know what? Of course, that can be estimated. If I want to determine the parameter, that will be determined from the sample taken from the population. I'm going to say that again. The parameter value will be determined from the sample taken from the that same population. But you know what? The question now is, what are the methods? What is the best method that we can use to obtain this parameter? Take a look at this now. But let's first understand properties, the characteristics of this probability distribution. This is a uniform because of this, you know, 1 over b minus a, right? If you remember, continuous uniform, 1 over b minus a. But here, a is 0, b is theta, and that is why you have 1 over theta, right? The f of y is 1 over theta. The CDF is that. And of course, the expected value of y is that. Of course, you know, for continuous uniform, expected value of y is a plus b divided by 2. I think you remember that from the lower level statistics. And of course, the variance is actually theta squared over 12. You know, from the lower level statistics, I think the variance is b minus a all squared divided by 12. Okay, all right, now a is 0, B is theta. That was why we got theta square over 12. Does that make sense? Now you know the expected value of, now take a look at this. It means if my random variable follow uniform with parameters 0 and theta, expected value of y, if I want to find the mean, is theta over 2. If I want to find the variance, it's theta square over 12, which means getting the mean, getting the expected value of y, getting the variance of y depends on theta. That means that we can't go forward without figuring out the values of the parameter theta. Any question? I think I need to, why I'm trying to tell you reason why we do what we do. We don't just do what we do. There's a reason why we do what we do. Now, I told you that moving forward actually required, we need to be able to figure out the values of theta. Now, nobody goes into research with an empty mind. We always have something in mind. Take a look at this. We have a proposal here. Two ways that we suggest that will give us the value of theta. The first one, and that was why you can see that I call them theta cap 1, theta cap 2. That's what we think about. The theta cap 1 is 2y bar. The theta cap 2 is the maximum of the sample that you take, like maximum of y1 up to yn. Now, these are the two estimators that are competing now. Okay? These are the two estimators that are competing now. And if I really want to know the one that will do the job, then the reason why I love statistics so much is because statistics gave us opportunity to evaluate, gave us opportunity to be able to investigate which one is better. Now, and that is the reason why we can compare them, apart from investigating whether they are unbiased or not. I told you the other time, an estimator may be biased. That doesn't mean it's a bad one, even though we're looking for the unbiased. Because we may not get unbiased at all time, but that's okay. The most important thing is efficiency. And how do I get efficiency? Is comparing the mean square error of unbiased estimator with that of and that was why we said find the mean square error. There, finding the mean square error of the two is at the end of the day, we'll be able to compare which of the estimator is better. But you know what I want to do now? The last example that I walk you through, I go by way of a simulation where we think of a value. The value that we actually think about the other time may not even be a true value. But the essence of thinking, is that, okay, let us see the approach that we're going to, do, that we converge to the one that we actually choose. But what we want to do now, we want to approach this from a theoretical angle. I'm going to say that again. We want to approach scenario from theoretical angle. What do I mean by theoretical angle? Let's first start by investigating whether the theta cap 1 and theta cap 2 are unbiased or not. That is where we're going to start from. Excuse me. Now, I need you to take a look at this. If I want to investigate for unbiasedness, then I need to take the expectation of the estimator. When I take the expectation of the estimator, and if that gives me the true value of the parameter, then I'm actually going to say that's unbiased. Let's take a look at that. Theta cap is what? 2y bar, right? Expected value of 2y bar. 2 is a constant, so it's going to come out, right? Okay. So we are here now. Give me one. Let me use a point, huh? Okay, so we are here now. And you know what? Expected value of y bar is the same thing as expected value of y. Okay, we know that. Okay. Now, what is it? You now go back to the distribution. Okay. You go back to the distribution. What is the expected value of y of the underlying distribution? You already given, you already know that. They say the value of y is theta over 2. That means you need to know the expected value of y and the variance of y of the probability distribution of the population. Now, that's what I'm going to plug in here. Okay, you can see I've already plugged that in, mathematically speaking. That now give me theta, right? Then that's shows that theta cap 1 is an unbiased estimator. Okay, now if the expected value of an estimator is equal to the true value of the parameter, then that gave us an indication that the bias is going to be 0. So when bias equal to 0, then it means that estimator is unbiased. That's what it means. Any question? Any question? You're good, right? Okay, let me say this. Because of my experience in teaching for more than 15 years now, when you are in my class, make sure you are focused. Don't attempt to do assignment of another class in my class. This class is actually contain a lot of notations, and it requires your 100% concentration. The moment you don't understand, ask question. That's no problem. That's why I'm here. Okay, now we're still focusing on theta cap 1. What is the next thing to do? The next thing is to obtain the variance, right? Then the variance of 2y bar. You remember? 2 is a constant, right? That will be 2 squared, variance of y bar, right? It's going to be this, right? Oh, what is the variance of y bar? The variance of y bar will be variance of y divided by n. Okay? This is this. You see that? Then you now go back. What is the variance of y according to the distribution? Take a look at that. Theta square over 12. That's what you're going to plug in now. That's what I'm going to plug in. Okay? I've already plugged that in here. And that gives me this. Any question? Who doesn't understand how I got that? In the numerator, the variance of y, I've already plugged in, okay, the variance of a random variable, okay, according to that distribution. Now, I want to find the mean square error. Of course, don't forget, according to Rao-Blackwell theorem, the mean square error can be written as, it's equal to the variance probably square of bias. Go ahead. The variance of y over n here. Because the variance of y bar is the variance of y divided by the sample size from statistical theory. You remember we did that before when we say, let me remind you, variance of y, sigma square, right? Variance of y bar, sigma square over n. The sigma square itself is the same thing as the variance of y. That's a good question. Now, since the bias equal to 0, the mean square error of an unbiased estimator will also be the same as the variance. Okay, we are done investigating the first estimator. Any question? Go ahead. Oh, that's a good question. These are given. You can be given any set of we have different, we have so many estimators. You're like so many strategies. Like your own strategy may be different from mine, may be different from now. The question now, let us investigate which strategy is going to do a great job. That's a good question. Yeah. Okay. Now we have done, we've investigated the unbiased net property of theta cap 1. We've also obtained the mean square error. Now the next thing now is to shift our focus now to theta cap 2. Now, when you take a look at theta cap 2, okay, theta cap 2 is trying to say, okay, you know what, go into that population, take a sample size of n, y1 up to yn, okay, and we are interested in the maximum. But let me tell you this, because we're going to go into this population several times, right? There will be so many maximum. We're going to have more than one maximum. Go ahead. Oh, how does mean square error different from? Oh, how does mean square error different from least square error? Oh, that's a good question. You know, the when you talk about the least square error, you actually they're more or less the same, except that the least square error is actually being used in modeling. Like maybe you're talking about regression and you want to get the values of regression parameters, and um, you want to get that in a way to minimize the total unexplained variation. So the word least means you want to settle for the minimum of the square. So it's kind of very close. But under the mean square error is more or less like, you know, the square, the average square of the distance between the prediction and the true value. That's a good question. Okay, now we want to focus on this the second estimator, theta cap 2, and they said is a maximum, right? And I put it to you. Uh, you know, we normally assume we go into the population several times, right? Let's say 1,000 times, right? At each time, maybe I go into the population first time, I'm going to get maximum, right? I go another time, that will be another maximum, right? There will be so many maximum. Therefore, maximum become a random variable. Anytime you hear maximum statistics, minimum statistics, your mind should go to other statistics. 4101, I think chapter 5 or 6. You can check. That's in textbook. Other statistics. The idea of other statistics is going to be used. Let me tell you this. Go ahead. Yeah, because this is what we normally do. We normally believe, even though when we are doing research, right, we go into population once, right? But the way this is our thinking, we actually go into that population several times. You remember when I was doing simulation, right? Like for the first time, I take my sample size, I get a value, right? I go into the population again, the same sample size. And that is the reason why we normally think that if 1,000 investigators they are working on the same thing. They take the same sample size from the same population, they will have different values. Therefore, that is the reason why sample mean is a random variable, because it varies. Does that make sense to you now? Now, the same thing applicable here. Maximum is not just going to be one maximum. There will be several maximums. Now, you know what I'm going to do? I'm going to save you of all this. I'm going to save you of all this. You're going to see the way I'm going to give you a formula. But let me first talk about maximum, minimum. Let me tell you this. In the Second World War, the other statistics was actually used by the Allies that fought against Nazism. And I'm going to tell you how they captured some weapons, some Nazis weapons, right? The Nazis weapons, all those weapons have serial number, right? Now, you know what the Allies are trying to do? They want to figure out what would be the maximum numbers of weapons produced by the Nazis. You know what they did? And they don't want to send somebody that will spy, because somebody that will spy, may not give them a reliable result, because the Nazis may try to inflate the number, just to scare the enemy. You know what they did? They used the idea of other statistics. Now, this is what happened. Let's say they look at what they capture, and there was the weapons actually have maybe 9, okay, or 71, 169, okay, and 342. Now I'm just using an example now. These are 4 weapons, right? 4 weapons, right? Now 9 is not going to be the minimum, but 9 is the minimum in our sample here. 342 is not going to be the maximum, but 342 here is the maximum in our own sample. Now, do you know, with this data, we can on average predict what will be the capacity of weapons in Nazi's arsenal. So because of that, we have a distribution for smallest, we have a distribution for the largest. So if I want to figure out the maximum, then I will use the distribution for the maximum. So that when I have the distribution for the maximum, I will be able to use that distribution to figure out the mean of the maximum, the variance of the maximum. Does that make sense to you? Now, it is that same idea that I want to use here. But you know what I needed to write down, okay, is this. The distribution of the maximum, okay, I'm going to say G of xn, subscript n, because I need to first ordered before I get the maximum. I need to order my observation equal. Okay, I'm giving you the formula now. You can write it down. Sample size, okay, the CDF. Of course, you know CDF. The CDF of that, okay, raised to power n minus 1, raised to power sample size minus 1, then everything multiplied by the PDF. So this is the distribution of the maximum. Okay, G of Sn equal n, CDF raised to power n minus 1, then multiply by the f of s. Now, the moment I know this, you know what I'm going to do now? What is the CDF? What is the CDF? What is the f of s? You've already given here. Do you see that? 1 over theta x. All what I'm just going to do, 1 over theta x. Okay, so all I'm going to do is just like, I'm just going to write G of X, okay, equal, okay, I'm going to write N, then into X over theta, okay, raised to power N, raised to power N minus 1. Then what is f of X? 1 over theta. 1 over theta. Let me tell you this. When you simplify this guy, see N, the CDF, raised to power sample size minus 1 multiplied by the PDF. If you simplify this guy, this is going to be your final results. That will be your final result. That guy now become the probability distribution of the maximum. Now that I have the probability distribution of the maximum, if you look at the method that I use in the material, I first go through the CDF. After getting the CDF, I differentiated the CDF to get the PDF. But if you don't want to go through all of that, the moment you know the formula of the maximum, plug in the CDF and the PDF, you're actually going to find yourself here. Okay, if I find myself, if I go there now, then every other thing is easy. I can find the expectation, okay? And when I find the expectation, that will enable me to investigate for unbiasedness. Then I can also go ahead and find the variance. Now, I want to find the expected value of that. Now, I'm going to use this. X, f of s, yes. What is my f of s? What I derive. At the end of the day, you see what you get? You see what I got? I got n over n plus 1 theta. Of course, that is bias because that does not give me theta. It gives me n over n plus 1 theta. Okay? Now, which means I can calculate my bias now. If I want to calculate my bias, look at that. If you want to calculate your bias, what do you get for the expected value of theta cap 2? N over n plus 1 theta, then minus theta. Now my bias is negative 1 over n plus 1 theta. Bias could be negative or positive. And that is the reason why if you want to find the mean square error, you need to square it. Statistics is interesting, right? Is there anyone here who's not enjoying my statistical party? Anyone? Do not hide your feeling. Okay, now the conclusion is theta cap 2 is biased. But let me tell you this. If the sample size is so large, let's come to this bias here. If the sample size is extremely large, right? We expect the bias to be 0. In that situation, that bias will be called asymptotic bias, which means initially it was, asymptotic unbiased, which means initially it was biased. But when you take a sufficiently large sample, it now becomes unbiased. Does that make sense? So that is what we mean here. Okay, now we've investigated that. Then we need to find we need the mean square error for this theta cap 2. But if you want to find the mean square error, you need to first obtain the variance. Now, I want to find the variance now. You remember this formula? Expected value of theta cap squared minus expected value of theta cap all squared. Okay, now which means I've already gotten. I've already gotten this guy. I just need to square it, but I need to go back and get this from the integration using uh the the um the probability distribution of the maximum. At the end of the day, this is what I got as a variance. I got this guy as a variance. Now, when I got this as a variance, theta cap 2 is a bias estimator. Okay? Then I need the mean square error. Now, the mean square error, okay? You remember? There's a formula. I put the variance that I got plus the square of the bias. And what do I have now? Okay, this is what I have as a mean square error. Now, I want to compare unbiased estimator with a bias estimator. Theta cap 1 is unbiased. Theta cap 2 is biased. Okay? Now, how do we compare them? How do we know which one is better? If you want to compare them, we can do the ratio. You know, when you see the mean square error of theta cap 2 divided by the mean square error of theta cap 1, when we simplify that, we got this guy. Now, I want us to do something now. You know, when I find a ratio, if you give 1, what does it mean? They are equally potent, right? Okay. But if the ratio is greater than 1, it means the numerator is bigger, right? If the ratio is less than 1, then it means the denominator is bigger, right? Now, let's take a look at this. Let's try with a sample size of 1. Of course, no reasonable researcher will take a sample size of 1. Well, let's just try this with sample size of 1, plug in 1. Oh, that's going to give you 1 ratio, right? It means when you take a sample size of 1, they are the same. Okay, let's go. Let's take a sample size of 2. 6 times 2, 12, right? I also get 1, right? Let's go to sample size 3. I want to believe from 3 and above, you will notice something there. Now, let's start from 3. 3, the top one is going to be 18. Okay? 3, that will be if n is 3 here and it's 3, I think that will be 4 times 5, right? That will be 20. 18 over 20. 18 over 20 is less than 1, right? 18 over 20 is less than 1. So which means when the sample size, and that was why by the time the sample size go to infinities, you expect the whole of this to tend to 0, right? Because of that. Look at what I said. Because when the sample size is 1 and 2, they are equal. Okay? If I want to conclude, then I need to be cautious. Look at what I said. Theta cap 2 is asymptotically. If I don't put asymptotically, I'm wrong. Because it is not at every sample size that the theta cap 2 is better. The theta cap 2 is only better when what? When the sample size is large. Any question? Any question? Okay. Now, if we do a simulation, let's assume that you assume your theta to be 2. Okay, maybe you assume your theta to be 2 and the sample size is 100. Okay, of course, sample size 100, you expect that theta cap 2 will perform better because even theta cap 2 start performing. Go ahead. Yeah, it's asymptotically better because the ratio is going towards 0. And if the ratio is going towards 0, it means the denominator is bigger. It means the mean square error of this is bigger than that. Exactly. Exactly. And that was why I became so cautious. Look at the way I use my word. I said, this is only going to be better than this in case you are working with a sufficiently large sample. Because by the time we started checking from sample size 1, 2, they are equal. There's no difference between them. Okay, now, this is the histogram. When we perform simulation, when theta equal to 2 and n equal to 100, you can see, okay? You can see that one, you can see that one. Now, what are the common unbiased estimators that we talk about? These are the common, okay? These are the common one. Sample mean, sample proportion, the difference of the means, the difference of the proportion. Those are the common unbiased estimator. I know you've come across a t-test, right? T-test for one population, for two population. You test difference of means, difference of proportions, right? They are unbiased. Because, excuse me. So because in the end, when I take the expectation of them, they're all going to be equal to the true value. That has been mathematically proved and statistically observed. But there's something I wanted to take notes. Take note of this. Look at the standard error. Don't forget, if the variance of y is sigma squared, the variance of y bar is sigma squared over n. What will be the standard deviation? The standard deviation of y bar is the same thing as the standard error, which is sigma over root n. I show you the one for proportion the other time. I show you the one for the difference of, of means, and the one for difference of proportion. Please take notes. Now, I want to focus on the mean now, mean. We normally talk about mean all the time, mean, average. Why 1 up to yn I deal with mean, mu, and the standard deviation? Of course, this is the sample mean, right? Sample mean is an unbiased estimator of the population mean, okay? And the variance of that is sigma squared over n. Now, if you go to proportion where we're actually having two possible outcomes, you remember the other time where we defined that, and each of that is going to follow Bernoulli. The mean is that, the variance is that. If I'm no longer talking about one trier, if I'm talking about the sum of the Bernoulli, that will become binomial. You remember? If that become binomial, what of if I'm interested in the average? Sum, that would be sum over n, right? Then, which is going to be this guy, which means, do you know that P cap is the same thing as Y bar? P cap is the same thing as Y bar. So if sample mean is an unbiased estimator, then P cap is also going to be an unbiased estimator because they're equal to each other. Now, because of that, because of the fact that I know if the set value of y equal to P, expected value of Y bar also going to be equal to P, and I know P cap is Y bar, then the expected value of P cap is going to be equal to P. The variance of P cap is actually going to be the variance of Y divided by N. What is the variance of Y? P into 1 minus P. So that is why you have P into 1 minus P divided by N. If I now want to write the distribution, oh my God, distribution will be very easy to write because I already know the mean of the estimator and I know the variance of the estimator. What I'm just going to write here is P cap approximately follow normal distribution, okay, with the true parameter P as the mean and the variance to be P into 1 minus P divided by N. That is the distribution. And of course, you know when this is going to happen. You remember what we did before for very large sample. Now, let's go to the difference of means, because at times we may want to compare whether there's a difference between means in two populations, and we want to compare, is there any significant difference between the average household income in the United States and Canada? The two countries are independent. Then I'm going to take sample from United States, and I'm also going to take another independent sample from Canada. Now, the mean income exists in the United States. The standard deviation of income exists in the United States. The mean income exists in Canada. The standard deviation of income also exists in Canada. Now, what am I looking for? I actually want to estimate the difference. But let me tell you, if I can get, if 1,000 investigator should go into United States population, and 1,000 investigator also go into Canada population, they're actually going to have different values for this difference. Difference of means now become a random variable because it varies. Now, but you know what? If the sample mean for United States is this, we know that the expectation of that is going to be true mean. It's unbiased with this variance. If the one for Canada is this, we know that the expectation of the Y bar for Canada is going to be true value, and the variance of that is this. Then do you know that because of the fact that this guy is a random variable, there are so many of that, then I will begin to look for what is the average. Expectation means average. Then I can also talk about what is the variance of the difference. Of course, you know what happened here. The first one will be mu1 minus mu2. And the second one is just going to be adding this guy to this guy. The covariance will be equal to 0 because the Canada and the United States are independent. Okay, now, that's about the difference of means. Now, coming to the difference of proportion, this is where I'm going to stop today. I'm going to explain this, and I'm going to start the slide 16. We're going to start from slide 16 on Friday, but I'm going to explain this. I think I have like 5 minutes. We also talk about difference of proportions, right? We may want to compare. Oh, let me come to politics. The proportion of votes received. There are two major political parties in the United States, Democrats, Republicans. Then I may want to see, is there any difference between the proportion of votes received by the two parties? Okay. And maybe I actually, they have so many elections. So what I'm trying to say here, why one, I need people. Okay. If I want to ask whether I'm going to have, do you vote for Democrats? The very first one is going to say, why I choose Y1 or to YN. I'm going to be asking them, do you vote for Democrat? Going to say yes. They will say no, yes, no, yes. That follow Benoni. The second one here, I want to focus on Republican. Oh, do you vote for Republican? Yes, no, yes, no, yes, no. That also follow Benoli. What am I seeking to get? I'm seeking to get the difference. Okay? And I know that the expectation of the difference is going to be the true value. Do you know the true value that I'm actually looking for is this guy here? But there's no way I can get that. I'm limited by budget. We don't have resources. So the P1 cap, that is the formula. That is the expectation. This is the variance. Take a look at that one for this, that for that, that for that. Of course, if I want to get the difference, the expectation of the difference now, just going to be P1 minus P2. Okay? If I want to get the variance now, it's just adding this guy to this guy. Any question before I go today? Any question? Oh, let me tell you one thing before I go. I have never seen any equation in mathematics and statistics that would scare me. You know why? It's not as if they are not complex. You know why they are not going to scare me? Because I will pay attention to what is behind the equation. The moment I understand the meaning of each symbol, the meaning of this, each note, you can see I've been relating this to Canada, United States. You hear about all of that every day. There is no way that equation will be complex. You will figure it out because you know what happened behind the scene. Okay, make sure you all stay safe and have a lovely day. We're going to see you on Friday. Give me 1 second.